to Bedtime Mathematics. Today we're going to be talking about the Wronskian. What the Wronskian is it's a way to find if a set of functions is linearly independent or dependent. And so what we have here is we have the notation of W for Wronskian, and then you have your number of functions all the way to the nth. And then then you set up a matrix to then solve the determinant, and to solve a matrix, or the setup for the Wronskian in this matrix is a style of your functions in the original form on the top going across the first row, and then in each respective column for that function you take the derivative and then you keep continuing the number until the n-1. So like let's say you had to take to like the 7th or 8th derivative, so you would take all the way down until the n-1. So in most cases, in the cases that I've dealt with, you don't usually deal with too many. I usually get to work with 2x2 matrices, which is nice for determinants. So yeah, so let's take a look at an example of actually using the Wronskian. So for our first example, we have two functions, x squared and x, and to find the Wronskian of that, we are going to put it into a matrix. So the matrix will consist of x squared and x. And so because we only have two functions, our n is going to be, it's an n-1, so we're only going to take one derivative. So we're going to only take the first derivative of each. So we're going to have 2x and 1. So now that we have that, that is our 2x2 matrix that represents these two functions. So now if we take the determinant of that, we multiply the two corners. So we have x squared times 1. So x squared times 1, and then minus x times 2x. So this is our basic method of finding the determinant. The formula for that is simply AD minus BC in standard form. So the matrix would go A, B, C, D. So if you see, I followed the formula here. X squared is A, 1 is D. So there's A times D minus the product of C and B, or B times C. Same thing both ways, right? So we have 2x times x. So our final answer will become x squared times 1 is x squared, minus 2x times x. So the two x's come together to make x squared, so it's a minus 2x squared, and if we have 1x squared and we take 2 more away, we are left with a negative 1x squared. And now we have just solved our first Wronskian, and by this result of negative x squared, we know that the set of functions is in fact linearly independent because the answer here is not 0. So if this thing here was 0, it would be dependent. We call a linearly dependent solution, or set of functions. But because this is not 0, it's independent. So that was a relatively easy example. Let's take a look at another one. So in this second example, we see that we now have 3 functions. And so what's going to happen is that when we set up our Wronskian, our matrix is going to contain 3 functions for each column, right? So now it's going to be e to the x as the first column, e to the 2x, and e to the negative x. And so if you remember our standard formula before for the how the whole Wronskian is set up, you're going to notice how we actually now need to take the first and the second derivative because there's 3. So n equals 3, and then this last part down here of the matrix, the bottom row of the matrix, is n minus 1. So it's 2. So we're going to take 2 derivatives. Alright? Did I spell derivatives? I don't think so. Anyway, so derivative of e to the x is what? What is derivative of e to the x? Just e to the x, right? And then same again. So then derivative of e to the 2x is 2e to the 2x. And if you're rusty on this, feel free to refer back to the beginning charts of your textbook that say this. And then we take the constant 2 up here, multiply it again by the constant out front, so we have 4e to the 2x. Alright, and so then this last column, taking note that there's a negative 1 there, so it'll be negative e to the negative x. And then down here we'll take the derivative again of this, so then 2 negatives multiply down to make a positive, so then we get back down to e to the negative x, and we take note that we never change the exponent of this e raised to something when we take the derivative of it. Obviously, if we took the derivative of x squared, we decrease the square down to a 1, but because this is e, we leave it alone. So, this is our 3 by 3 matrix. And so what we have to do is we need to take the determinant of this to actually, see if the functions are linearly independent or dependent. So, to do that, we have to know how to take a determinant of a 3 by 3. And so the first step is to basically just pick something. And basically what you're going to do is you're going to pick a row or a column. I like to do the top left, so we'll take this one. And so the first thing you have to know is that there's a checkerboard pattern that lies within a 3 by 3 matrix, and you assign positive and negatives to it. And I'll explain what I mean by that. So what I mean is this thing has a plus sign associated with it. This has a minus. This has a plus. And I say it's a checkerboard because then it's minus, plus, plus, minus, minus, plus. So you see adjacent, you see it's never the same. It goes plus to minus to plus, plus minus to plus, plus minus to plus. It's the same pattern everywhere, and that's where we get the checkerboard. That's why we call it that. So, keeping that little thing in mind, we will now take the, let's get a new color here. We will now take the determinant of this. And so to do that, we will grab something and put it out front. And what I mean by that is, we will first take e to the x. So, e to the x. We have that. And then what we do is we assign, oh, and another thing too, I forgot to mention, the plus sign. So this is positive. So this e to the x will be positive. And regardless of if this was positive or negative, we're going to additionally tack on a positive sign. And we'll see a better case of that later on. So this is this. So then what we do is we write a 2 by 2 matrix that has nothing to do with e to the x. And what I mean by that is I don't want it to intersect with e to the x that I have circled, and so anything in the line or in the row or the column of e to the x we don't include. So what we'll end up with is a matrix of these 4 things here. Okay? And we're not looking at the positive and negative signs I wrote in red anymore. We don't care about that when we write this 2 by 2 matrix. So we will end up having 2e to the 2x and then negative e to the negative x. And then same for down here, we will have 4e to the 2x and e to the negative x. And then that's our first part of this process. And so now what we do is we actually simply do this process again, but we're going to do it for the second term in this row. In this row, I mean this. So it's now, instead of looking at e to the x, we're going to look at e to the 2x. So let's circle or square this one up, right? E to the 2x. And so now we notice we have a negative sign associated with it, so we are going to put that right out in front. right out in front. It really hinders me being left-handed. I need to fix the setup here. So, negative sign. Next, then we just throw on that e to the 2x. E to the 2x. Now, our matrix is going to be everything that's not in the same row or column. So we're not going to look at this, and we're not going to look at this. So we have this T-shape going on here of stuff we're going to exclude. So we are left with these two things, and these two things. Let's box it a little bit. There we go. So we're left with this. And so we're simply just going to transfer it down into a 2 by 2 matrix. So we have e to the x, negative e to the negative x. We have e to the x, and once again we have, or a little different, e to the x, e to the negative x. So that's our second part. And now the third part is going to be the same approach, but we're going to be looking at the third. I'm erasing more of my matrix here, it's not good. Now we're just going to look at the third part of it. And when I say that, we mean we're just going to look at this third part of the row, the third term of the row. We're going to look at e to the negative x. So now, before we had e to the x, this tied in there, this tied in there, and then we're going to have a third one, which I'll write up in the top. Right in the top. So then our third one is going to be e to the negative x, and so then our matrix that is applied is going to be not looking at this row or this column, so we're left with this right here. Okay. Oh, one thing I forgot to take note of the plus or minus sign I have in red over here. So we have a plus, so let's plus there. So now we go down here, we have e to the x, and remember the red plus and minus signs here now we don't care about. We only care about them when we put them out in front of the matrix. Once we start making our 2 by 2 matrix, these don't apply anymore, okay? So we have e to the x, that's an e, I promise, 2e to the 2x, then we have e to the x and 4e to the 2x. Then 4e to the 2x. So now everything's kind of everywhere, so I'm going to erase, I'm going to do the math for each of the matrices and rewrite it quick, so then it looks a little better. So we're going to do that now, put in fast forward, and go. And we're back. So, what I did was I took the determinants of each one of these matrices. Simple 2 by 2, simple A, D minus B, C stuff that I covered in the first example. So, we're left with this. And so I leave it in this format because this is the product of the AD of this first matrix here. BC is the second part here, and that goes along with each part for each matrix that I have. And so I write it out in this way because there's a lot of little stuff that goes on, and I don't want to kind of miss it and mess up on a sign mistake. And what I mean by that is we have negative signs, you know, we have a double negative here because we're always subtracting, right? We're always subtracting when we do the determinant, right? And, you know, just some funky stuff going on. So let's turn that to a positive. Let's turn that to a positive. That stays negative. And so then now the next step is to just distribute out the, each of the, so the e to the x will go here and here. Negative e to the 2x will go here and here. And then e to the negative x will go here and here. So let's do that. So e to the x times 2e to the 2x. We add each of these exponents of 1. So we end up with 2e to the 2x. And then we bring this to the second part. And now this minus 4e is a positive 4e to the x. So we end up with plus 4e to the 2x. So we're definitely going to see some like terms here, so we can combine some stuff. This negative e to the 2x times 1 is just simply negative e to the 2x. Same thing over here. This is a positive 1, even though it doesn't look like it, but it is, I promise. So then this is once again e to the 2x. So then we look on to our third part involving our third matrix, which still is hanging around up here. So we multiply this by this, and so a negative 1x plus a 3x gives us 2x, and multiply the 1's by 4. So this product will be plus 4e to the 2x. And then our last one is e to the negative x times a negative 2e to the 3x. And this is a reason why I kind of write it all out, because we got negatives and different things. So we have negative 2, so it's going to be minus 2e, so 3 and negative 1, once again 2x. So, which is really cool, because every single one of these has a 2x in the numerator, or in the superscript, right? So these are all like terms technically, so we can kind of combine a little bit here. So we got plus 2 here, we got 2 minus 1's. So those two things are going to go away. So we're left with these three things, right? So this product, or the addition of 4 and negative 2 is positive 2, and plus 4 gives you 6e to the 2x. So that is the Wronskian of that. And because this number is not 0, then we can say that the solution of the functions we had initially, which if you scroll back a few minutes, which were some very different functions of e, you see that they are in fact independent because the result was not 0. So yeah, so now let's take a look at doing a Wronskian where the answer actually does come out to be 0. So let's take a look at that now. So I found a set of functions in my notes that I know for in fact turns out to be dependent. So let's take a quick look. So we have two set of functions. So we're going to let y1 sub x equal x. Pretty easy, right? Then we're going to let the second function, which we're going to call y2 sub x equal 7x. Alright, so now we're going to make the matrix to represent that. So we're going to have x in the first column and 7x in the second column. So compared to the last example when we had 3 functions, this is only going to be a 2 by 2 matrix, which will be nice, which means we only have to do one derivative of each. So the derivative of x is just 1. The derivative of 7x is 7. So now, if we take the determinant of that, we will find that we cross the multiplier, right? So x times 7 is 7x. 7x times 1 is 7x. And then we subtract the 2, right? And lo and behold, we get 0. Which means that the two functions 7x and x are linearly dependent because the value comes out to be 0 and not some random number like e to the 6x or something crazy. So yeah, so that shows a few examples of the Wronskian with 2 by 2 and 3 by 3 matrices, and expressing whether it's linearly dependent or independent. We saw examples of both. So yeah, I hope you enjoyed this video. Hope you learned something. Thanks for watching Bedtime Mathematics.